Greetings and thank you for joining our webinar. Thank you from the team here at Nautel Nav and Kenta. My name is John Whyte. I'm the head of marketing and product strategy for Nautel, and we welcome you, our worldwide audience today. I think you'll find this to be a very informative webinar. Let me kick things off by introducing our team and the agenda. So I have joining us today Hermann Zensen. He's the head of sales and marketing for Kenta. And so welcome, Hermann.
Hello.
And also Philipp Schmid, Nautel's Chief Technology Officer. Welcome, Philipp.
Hello.
So we've got a fairly packed agenda today. We had a lot of really enjoyed putting together the content. I hope you'll find it informative. So we're going to just do a quick review of the Navdat opportunity, and then we call this myths and misconceptions, but it really is going to be considerations to think about as you look ahead towards Navdat. So we'll walk through those, and then we'll take some time for questions and answers at the end of the presentation. And speaking of questions and answers, you'll find on your console a little green arrow, and that's where you take control to open up and close the console. You can use that to enter questions, and we may take some of those as we walk through the session, but mostly we'll save those for the end of the presentation. So just a couple of words about Kenta and Nautel. We have a very long-standing shared passion for things maritime and maritime communications. Nautel actually invented what we think of as the modern-day navigational beacon over 50 years ago. Our companies are located in Canada and the USA and in France, and we have over 20,000 deployments of transmitters worldwide, spanning over 5 decades. Some of the, I guess, why Nautel and why are we bringing this message to you today? We actually feel like we're fairly uniquely positioned to talk about these topics because we are the world's largest NAVTEX supplier, but also we are a supplier of high power transmitters and have very deep specialized knowledge in the area of digital transmission, whether that's DAB, DRM, or HD radio. And a lot of these technologies, as you see, are very inherent to the topic of Navdat. So with that, I'm going to hand it over to Hermann, and we'll take a quick walk through, a quick 2-minute review of Navdat. Take it away, Hermann.
Yeah, thank you. Good morning, America. Good afternoon, Europe, and good evening, Asia. Thank you for being with us. And yes, when we prepared, all three of us, the webinar, we found a very good report from the US Coast Guards about NAVTEX modeling. And this report was done after this El Faro disaster. So the El Faro disaster is, yes, what happened? It was a ship that left Jacksonville in Florida. It was in 2015. It's not so long ago, okay? And it left, and it headed directly into a hurricane. And after this, the ship sank. And the Coast Guards, the US Coast Guards, they did a deep investigation on why and what happened. And in particular, they wanted to find out if they got the NAVTEX messages. So they did some coverage planning on the NAVTEX, transmissions. And it turned out that almost for sure they got the NAVTEX messages, but still somehow they didn't seem to get the message. And the reason for this was that what they call a lack of situational awareness. It means, maybe you can show the next slide, John. If you look at a NAVTEX message, here we have a NAVTEX message from one of our engineers who delivered this. He's a radio amateur. You can see it's a 516. This is because of the software-defined radio. It should be 518. It's from Bermuda, okay, so you can receive it in Halifax. And this is a typical weather forecast. So, but as you can see, it's just text. And if you look at the situation for the El Faro, it was okay. They would probably have received a text like this, but the captain was not able to say, okay, this is the text. This is where I'm with my ship, and this is how I can avoid the hurricane. If and this is a little bit the expectation, we can show it the next slide, John. This is what the promise of Navdat is to deliver better data and content. it means typically maps. Imagine for the El Faro captain, you would have had a map with the situation of his ship and where the hurricane is. Probably he would have avoided the hurricane, and we would have avoided this tragic accident. Okay, so it is really about increasing situational awareness. Okay, and just come back to the other one, John, the first one. So the old way of doing this was, you see on the left side, you can see this is the plot. You have plot and text messages. The new way would be, we will have it, with good graphics integrated in the ship's active system. Okay, so the idea is that we introduce with NAVTEX digital communication and way better graphical information that are easier to use and easier to interpret. Okay, to increase situational awareness. Okay, go to the next one. Yeah. This is just a short summary of the advantages of NAVTEX. Okay, we have presented this already a little bit. Okay, so we can get enhanced range and reliability. Okay, so we will talk about the transmission range in this webinar. But then, as we are in digital modulation, we have several ways of increasing protection and get better coverage. And we can have higher data capacity. The whole idea is to transmit more bits, obviously, that we can have better data. We have multimedia capability, so we are not limited to any type of files. It can be text, it can be images, it can be vector files, video, even audio. Everything is possible. Okay, and we have flexibility on the frequencies. We talk a lot about the 500 kilohertz, but there are also other frequencies around 500 kilohertz that can be used now, and also in the HF. And yes, flexibility also that we get it into the ships completely integrated in the ship communication system. Okay.
Herman, I think you have some examples of the types of images that a lot of boaters are used to seeing these days through when in near shore. Let's take a look at those.
Yeah. This is an example we took from Windy. Okay. So this is a very popular application, and you can see in the Windy, you can see the winds. Obviously, this is the name of the application. So you can see the Atlantic with all the winds. You see immediately in the red zones we have, strong winds. Okay, so this gives you immediately an awareness and a warning on this. And the beauty of Windy is, if you look on the right side, you have all the charts. Okay, so you have different layers. Okay. So it's the same map with different layers, and you can have a wind map. And then if you look at the next slide, John, we have another slide. This is on the wave height. Okay, you can see we have up to 10 meters in the Atlantic, which is quite a lot. Okay, so all this information is very easy to transmit with NAVTEX. Okay, we also have another example. We took this, we uploaded this from the Canadian Coast Guards. This is an ice report. Okay, same thing. You have a map. You can immediately see. This was last week, by the way, and you can see yes where we are on the ice in the Arctic. Okay, and this is easy to understand. And if you look at the second one, this is a little bit more. This explains again very well the awareness. If you have on the right side, you see the map with the barrier. Okay, the red line. Okay, so it's easy to see on the map where we are on the red line. But if you look on the left side, this is the text. This is way more difficult to interpret. Okay. So the thing is that to deliver easy interpretable information to the ships. Okay. These are the examples.
Great. Thanks, Herman. So through the next section of the webinar, we're going to do I guess some comments that we may have heard from discussions that we've had about the topic of NAVTEX, and we'll provide I guess a little bit of a deeper dive as to the underlying understanding of that message. So this is the first one. We'll kick it off. So existing NAVTEX infrastructure can be reused for NAVTEX. I think, Herman, maybe that's yours for discussion.
Yeah. Well, if we discuss about existing NAVTEX structure, so we started like this. You should compare, first thing, compare the two spectra. It's the easiest to start. Okay. So we have a NAVTEX spectrum here on the left side and the NAVTEX spectrum on the right side. So you can see on these first thing, they're completely different. Okay, so completely different. You see the NAVTEX, we are on FSK modulation. Okay, which means you have a triangular form of the spectrum with ripples on it. Okay, it's 300 hertz broad. Okay, so it's the width of the signal is only 300 hertz, which is not a lot. Okay, so you have a small signal bandwidth. NAVDAT is different spectrum. You can see. So we have a rectangular spectrum. It's why we do have this. It's a very dense spectrum. There are multi-carriers. It's a multi-carrier. We will discuss this. We will show this later. So we have many carriers close to each other, and this is why you have this rectangular form of the spectrum. So it's a dense spectrum, and it can also be quite broad. You know, the reason for this is the broader it is, the more information you can transmit. Okay, so we have shown you the 10 kilohertz one, but typically we have different types of bandwidth in the NAVDAT system. So NAVTEX we only have one, which is 300 hertz. NAVDAT we could have, the smallest one would be 1 kilohertz. Then we could have 3 kilohertz, 5, and 10. Okay, if you look at it, the more bandwidth you have, the more difficult it gets for your existing system. Okay, so let's say 1 kilohertz is still okay, but 3, 5, 10, you're really on a big bandwidth here. And this has an impact on the transmitter design, on the transmitter you have to use, on the antenna tuning unit, and also on the antenna itself. It has to be, the antenna also has to be broadband enough to allow for 10 kilohertz to pass. Okay. So if you look at the next slide, okay. So it's, to sum it up, it is possible to it is possible. Maybe you can reuse your existing infrastructure, but you have to take care of two things: of the bandwidth and also of the peak powers. Okay, so it is the NAVTEX signal. The NAVDAT signal is how to say it? It's a digital modulation signal. So you have high PAPR, so high peak average power ratios. This means you have to take care of the power. You have a power problem and you have a bandwidth problem. So it's maybe you can use, but it's not very probable that you can reuse your the same infrastructure. And in any case, you would need to do a good audit on it to be sure to see exactly where you are on the bandwidth, where you are on the power that you can use on your existing system, and most probably you would need to upgrade it, or in other cases to do a separate infrastructure.
Yeah. So not straightforward. You need to examine your infrastructure.
Exactly.
So the next one we have is a 1 kilowatt or 5 kilowatt NAVTEX transmitter, can be replaced by a similar power NAVDAT transmitter. So if you have a NAVTEX transmitter today at a certain amount of power, you could replace it with a NAVDAT one of the similar power. Philip, maybe you have some comment on this statement.
Absolutely. With our background in digital modulation, this is a topic that comes up over and over again. How transferable is a transmitter from one standard to the next? So we first have to look at NAVTEX to get an understanding how different NAVDAT really is. So here's a couple examples of the NAVTEX modulation. 3 graphs on the left. The top one is just data. And it is, in this case, it's just a single bit information, 0 and 1. Binary information, that's sort of the input, and we have our carrier at 518 or 490 kilohertz, and that essentially modulates the waveform in 2 frequency components, a higher frequency and a lower frequency. Total deviation is about 170 hertz. But as we saw, the triangular shape confines the necessary bandwidth to about 300 hertz, but it really goes on technically indefinitely. But the majority of the power is captured within 300 hertz. But the key thing to note here is that you see it's a single sine wave. That single sine wave has a constant power envelope, which means that for a NAVTEX transmitter, if you buy a 1 kilowatt NAVTEX transmitter, you also have 1 kilowatt peak envelope power transmitter. So peak envelope power is the same as your average power, and that's about to change. So if you go to the next slide. So I've created this little demonstration here. Let me walk you through that. So if we move to NAVDAT, and Hermann already mentioned, NAVDAT can have many carriers, many individual sine waves, up to 229 in a 10 kilohertz mode. But if you look at just a single carrier on the left plot, that's similar effectively to NAVTEX. And that one carrier, again, single sine wave, and I'm showing the power envelope here, just to be clear, in all of these plots, both the negative and positive. So it would look similar to what you would capture on an oscilloscope, but it is power, not the instantaneous voltage waveform. But if you have a single carrier, it's very similar to NAVTEX, a constant power envelope. Then if you move on and add more carriers together, that's on the right in the next plot, and I'm showing 3 carriers. I'm wishing I had just shown 2, because if I had shown 2, you would see a nice sine wave riding on top of the envelope. But even with the 3 carriers here, you can kind of see the 3 frequencies as they constructively add and subtract from one another, depending on the phasing of those waveforms. So as you add more carriers, so let's say 23 carriers in the next plot, you'll see there's more and more erratic envelope characteristics being developed. Oh, just back there.
Sorry.
No problem. With the 23 carriers, you can already see that there's intermittent larger peaks. And as you add more carriers, up to 229 carriers, as we mentioned, the signal becomes effectively very noise-like. You're almost transmitting a noise-like signal. And some of the power peaks in that signal can be 10 times higher than your average power. Now that's perhaps a little bit conservative. The standard also talks about a 10 dB back off, 10 dB overhead. And 10 dB is convenient because it's 10 times. It makes the conversion real easy. Now, our background here at Nautel with digital communications, we do focus on what we call peak to average power reduction. So which are algorithms that allow us to target the peak powers in a transmitter, reduce them a little bit, and that allows us to get more average power out of a transmitter. But the message here really is you need to use a transmitter that can handle the peak power of the signal. So no longer does average power equal peak power apply here. You need to now back off and reduce the average power almost by a factor of 10. So if you started with your 1 and 5 kilowatt, well, now you have to reduce your power down to 100 and 500 watts. And we will have a look at that, what that means in terms of coverage in a little bit. But yes, could you run Navdat on a NAVTEX transmitter that is Navdat ready? So technically, yes, but you're going to suffer in coverage. So there's limited use in having a Navdat ready transmitter today because the power levels are just so different. Perhaps in an emergency case, you could switch a NAVTEX transmitter to Navdat, but you're not going to be able to deliver on the promise of all the, the powerful coverage, the extended range that Hermann was talking about. So you'll have a choice. You need to really look at whether you want to keep similar range to NAVTEX or increase your power. So there's really a 10-to-1 rule of thumb here. So instead of a 1 kilowatt peak to average or peak envelope power, you probably should be looking at a 10 kilowatt peak envelope power. If you're looking at 5 kilowatt, then it's 50 kilowatt peak envelope. So those are different transmitters, and they certainly exist. We have, we'll get to that a little bit later, but certainly Nautel has the experience with those power levels, no problem. And we'll get back to that in a little bit.
Okay, thank you, Philip. So the next proposition here is that Navdat transmit at 25 kilobits per second. Hermann, is that one you want to comment on?
Yes, this sounds like a big promise. 25 kilobits. I've heard this very often. It's a little bit more complicated than that. Okay, this is linked to the the structure of the modulation. So yeah, Phil has talked about the PIPR thing, and if you look at in the time signal that that it's like a noise-like signal. Here we have a little bit of different representation. So the digital modulation, we have multi-carriers up to 229. Okay, and each one is modulated by phase and by amplitude. Okay, so once this is set, you can put this into a diagram, okay, with the amplitude and phase, which is kind of a complex number, you could say. We call this constellation diagram. Okay, so for example, let's imagine you have one carrier that is modulated only by phase, same amplitude and modulated only by phase. This is the 4QAM. So with this, you can have 4 different states, yeah, and you could transmit 2 bits per carrier. Okay, if you use 4 QAM, this is what also we called before QPSK. Okay, if you want to transmit more bits, then you would need to add, more points in your constellation diagram. So the next typical thing that we do in digital modulation would be 16 QAM. 16 QAM, you can see, so you have 16 different states. Here we modulate amplitude and phase, and you can transmit 4 bits per carrier. And if you want to transmit even more, then you can go and say, okay, we have 64 QAM, and here you can transmit 6 kilobits per second, 6 bits per second, per carrier, sorry. So what does it mean? So you would say, okay, that's fine, then let's only use 64 QAM. This is where we can get the maximum of bit rate, because here you can transmit the most number of bits. Yes, but there's a trade-off again, because the 64 QAM is way less robust than a 4 QAM signal. So you can see this in the signal-to-noise ratio. Okay, the signal-to-noise ratio is something like 14 dB, and you will be at 22 dB for 64. So it means it's very easy to disturb a 64 QAM signal, and you get more and more errors in your transmission. Okay, so this is why you can show the next slide. Yeah, this is why you have in the standard defined many different bit rates. Okay, so this is just a table, the table 24. It's in one of the annexes. This is about the data channel, and the data channel it's encoded, special encoding, and you see you can have something between 300 kilobits from 300 bits, sorry, to 29 kilobits. Okay, 300 bits. So 300 bits. We mentioned that at NAVTEX we had 100, so we are only 3 times more here in the, let's say, then you're in the most robust mode on the smallest bandwidth. So what is so the bit rate depends on the bandwidth you use. It depends on the modulation scheme you use. And then you have another line here, which is called the channel coding, which is LDPC in this case. So you have also different modes. Basically, this is about adding some bits to correct other bits that have been transmitted not the right way. The more bits you add, the less useful bits you have. Okay, and this is so. This also means the less bits you have for protection, the more data you can transmit, but the signal is less robust. So in theory, you can transmit 25 kilobits. This is possible, okay? And there is a mode with even 29, but the standard defines something between 220 kilobits, 0.22 kilobits, sorry, to 29 kilobits. And it depends on bandwidth, power, modulation type, and channel coding. So it's not exactly 25 kilobits. We are in the optimistic scenario with a, it's possible, but we have to have very good infrastructure then also. Okay.
Thanks, Hermann. So the next consideration is NAVTEX and Navdat have comparable range and coverage. Starts to be a bit of a theme here, it seems. Philipp, I'm going to hand that one to you, I believe.
Absolutely. Yeah, we can go to the next slide. So thanks, Hermann, for explaining the various data trade-offs. And I guess the key message is, if you want more data, you need more power. That's really what it comes down to. It's not just more power and bandwidth, like you said. So first, let's have a look at NAVTEX coverage planning. There's some literature that you can find on NAVTEX. And there's just ITU guidelines on the left that go through how to do some basic predictions in terms of how far the signal will go across water. And the key thing here is that the reception is typically limited by man-made noise or shipboard noise. It's not like Nautel coming from a broadcast background where multiple radio stations will be on the same channel, and it's a co-channel. What is different here is the all of the limitations are essentially how much noise does the receiver capture, and will that drown out your transmission? And the other portion is atmospheric noise, which depends on geography, the time of day, the season. I should have also mentioned the salinity of the water makes a big difference in terms of how far the signal goes. So you have to do an analysis depending on the geography you're located. So we also have a technical report here prepared by John Pinks, our Chief Engineer Emeritus, that's prepared this report for Indian waters. And so you have to figure out what the noise characteristics are in what geography. And in this particular report, he found that a 3 kilowatt transmitter, and again, that's average and peak interval power being the same, NAVTEX transmitter, you would expect about a 389 nautical mile range. So that's having that sort of as a background, and even experience would show that even between 100 and 1 kilowatt NAVTEX transmission can go quite far. So for example, on this plot here, and that was taken from an excellent report for that was modeling navigational telex. And we've provided the link here. It's available publicly. You can have a look at it yourself. And the coverage analysis on the right was taken from that report. And what we're talking about next here is just an informative, not a complete analysis down to the nth degree, but just to demonstrate the sort of things you have to think about. So coming back to NAVTEX, this particular report here was investigating whether some of the transmitters in those installations could be reduced from a 2.5 kilowatt down to 1.5 or 750 watt level. And those are sort of the predicted contours. And maybe while we're on this map here, if you look at west 65 degrees, you see Bermuda just popping out here. That's where we picked up the transmission that Josh Merdling, our engineer, has picked up just this morning for us with the latest weather forecast in Halifax, just on the top of the map here in Nova Scotia. So you can see, with the right and receive antenna, and the signal goes very far. NAVTEX is a very robust signal. It is already digital. Some people might think it's analog, but no, it is a digital modulation that has been chosen to be super robust. So it creates a fairly long range. So moving on to the next slide. Still talking about NAVTEX here. Our report by John Pinks has suggested that a minimum field strength of 40 dB microvolts per meter, or that's 100 microvolts per meter in linear scale, is sort of a good edge number. Now, some receivers, or some ships will be able to go much lower than that. Some reports say they can go down to 20 or even 15 dBu, but now you're really talking about differences in the receiver implementations. So first of all, you need to kind of think who is your target audience for your broadcast. If you're talking professional Navy ships, although they would probably have a lot more electronic noise, I would imagine. But perhaps professional ships could probably go much lower. But if you're looking at basic fishing vessels, you might not be able to assume that it can get the very lowest signal. So that's one thing that's a little bit up for debate here as well. How far do you want the signal to go? But 40 dBu seems to be a good rule of thumb that we found. So in this coverage map over here, that's indicated by the green contour, and it's going to get a little bit tricky here. So pay attention to the fringe and the legend in the top left of that map, because I'm going to change those numbers a little bit in the next couple slides. But in this analysis, the green would give you a fairly good coverage all the way out, and the blue and purple would sort of be the fringe where you may or may not get transmission. And again, NAVTEX, same transmitter power, same transmitter size. So NAVTEX actually has excellent coverage today. Let's see how that compares to Navdat. So let's take the scenario here that we mentioned earlier. Can I use my 1 kilowatt or 5 kilowatt transmitter and simply run Navdat on it? Well, yes, you can. But if you look at the transmitter power level, it means you already have to decrease your transmitter power significantly in order to use the same transmitter size in the bottom line here. So that is your first hit to your coverage. So what I've done here then, if you look at the fringe and the legend of the map, really I've subtracted the appropriate dBus to reflect the drop in average power. So your field strength has decreased because you reduced your transmitter power significantly. Then the next thing is we've increased the bandwidth from 300 hertz to 10 kilohertz, as Hermann illustrated earlier. And what that really means is that your receiver will capture much more of the man-made and atmospheric noise. So therefore, it requires a greater field strength to overcome that noise. And we've run some of the analysis that are part of the guidelines. And if you really want to get to the high data rate mode at 64 QAM, your 40 dBu increase to 52 dBu. What does that all mean? Your coverage has reduced significantly. So it would actually be sitting, 52 dBu on that plot is not even showing up as a contour. So it would be well into the red at this point. So yes, you'll get high data rate, but only close in. And really the transmitter power is probably too low, except maybe emergency situations. But I think for the general case, simply reusing a NAVDAT ready NAVTEX transmitter is not going to be delivering on the promise of NAVDAT. So what can we do? Next slide. So of course, you would say, well, this transmitter power is way too low. That's not a fair comparison. So okay, let's say we'll bump it up to the same transmitter power output that we would have today. In our case, 750 to 1.5 kilowatts. Now that means you need a bigger transmitter already because your peak envelope power is now going up to 6 to 12 kilowatts. So you won't be able to reuse the NAVTEX transmitter anymore. So you'll need a bigger one already. So in that case, again, we're kind of keeping our 10 kilohertz bandwidth, 52 dBu, and now we can push it out to about the red contour. And again, installations change, different geography, you might get different results, but just back of the envelope, you could expect a much reduced coverage from the green coverage that we had before. And that's because we need a better signal to noise at the same power level. Okay, next. So we mentioned the different data rates earlier. One option is, well, going back to the same transmitter size as before, could we use an existing NAVTEX transmitter to extend NAVDAT at a low data rate? So in this case, we assume we reduced our 10 kilohertz bandwidth for NAVDAT to 1 kilohertz, and that cuts out 90% of the noise you're capturing. And we're assuming we're reducing the 64 QAM to 4 QAM, which makes it more robust. So we're estimating that would probably get you into a 34 dBu range where you could receive that signal. Another factor that exists, and I've mentioned peak to average power reduction earlier, as you reduce the 64 QAM to 4 QAM, peak to average power reduction will likely be more effective. So we get a little bit more power out of the transmitter. So instead of 90 watts, we could probably get 150 watts out of this transmitter. And that will allow you to push back the, your coverage back to probably not quite the same level as NAVTEX. It will probably be slightly reduced. However, you're going to take a very significant hit in data rate. You could be down to 300 bits per second. And that's really not much different from the 100 baud that NAVTEX offers today. So it's really not delivering on the promise of NAVDAT. So I think the best option, and if you move on to the next slide, we can overcome these challenges with more power. So in this case, we're widened our bandwidth again to 10 kilohertz. We've increased our fields, so that would maintain the same dBu numbers of 52 as before. By increasing to 10 kilohertz and back up to 64 QAM, now we're in the 19 to 29 kilobits per second range. The high data range that Hermann was talking about earlier. But our transmitter power has significantly increased. In this example, we would think it could be somewhere between 12 and 24 kilowatts. Perhaps, this might be reduced a little bit depending on requirements. So this might be the highest possible data rate. But one thing to think about here is that it really has pushed up our peak to average power and our power peaks into significantly high power numbers. Now, this might sound like a very high transmitter size if we compare to NAVTEX sizes today, but these are the power levels we typically install in medium wave AM broadcasts. We have installations up to 2 megawatts. So, you know, this is certainly possible. The technology exists. It is certainly doable, but it does require a rethink. Okay, perhaps next page. And again, you know, it comes down to this trade-off. And we're coming back to the same message here. Trade-off between bandwidth, power, and data rate. And maybe to put that a little bit into perspective is, you know, if you're running the full QAM mode and you're somewhere in the 6 to 10 kilobits per second, and we're assuming, I think, you know, so in a 10-minute block, you could transmit somewhere between 450 and 750 kilobytes. That's really not that many weather charts you can really put in. That's maybe 2 or 3. And then, of course, you need to figure out your power in order to get the coverage. And remember, if we go down to 1 kilohertz, well, now I don't know if there's even any room for any weather charts to be transmitted 10-minute slot. Maybe in longer slots, you might be able to get something through. But then as you go up to 60 and a 64 QAM, now in a time slot, we could transmit several weather maps. So it comes down to the requirements and the use cases that you envision are practical for your mariners, and you know that's kind of where we have to pass it over to the particular applications in your location and your jurisdiction. Okay, I think that's bringing us up to the end of that. So in summary, they don't have comparable range and coverage if we don't do the proper planning. So either we can achieve similar coverage with low data rates, but they don't deliver on the NAVTEX potential, or we can deliver similar coverage with high power, but that doesn't imply new transmitters, ATUs, antennas. Another question you might want to ask yourself is, well, maybe I can't achieve the high transmission power. Is it possible to build an extra site or two? Again, that depends on how far across open seas you have to broadcast, and you know, at some point you'll be limited to how far it can go with power. But it depends on the geography. So you need to look at your use cases and see what's practical in your market or in your jurisdiction. But the key thing here is, if you plan for NAVDAT today, then certainly we can switch a transmitter into NAVTEX mode, and you know, at the lower power level, get you the same coverage. So we can, you know, a NAVDAT first system can support NAVTEX. But if you plan for NAVTEX today, then NAVDAT will at best be limited.
Great. Thanks, Philip. And we're making good progress here. We're about 3/4 of the way through our content. The next one to consider here is there are NAVTEX transmitters that can later be converted to transmit NAVDAT. And I'll actually speak to that one. And it's probably going to be a little bit of a repetition of the theme that you've been hearing here. If you think of, for AUKUS comparisons, assuming that you have good bandwidth through your transmitter and antenna and matching unit, you really have 3 dials that you can turn. So power, range, or the data rates. And so if you start off with low power, then you can either pick range or data rates. You're going to get one or the other. So if you compromise on your data rates, you might be able to get some reasonable range. If you compromise on your range, you can get higher data rates. I guess the reality is you can't get both. So in a perfect world, you'd have high power that would get you high range and high data rates. So are there transmitters that can be converted to transmit NAVDAT? Yes, technically, but you may not achieve the goals that you were hoping for. You need to take that broad view of what power do you need, address the ATU, and address your antenna system. So moving on, we're at 6 out of 7, I believe, of these things to consider. So NAVDAT will replace NAVTEX. I think maybe Hermann, you had signed up to speak to this point.
Yes, well, we have here one slide, which is a quite interesting slide. We took from the standard all the NAVDAT subject message codes, okay, that are defined already in the standard. So you can see there are many, many, many. So we have, for example, the meteorological one with the ice reports that we have shown to you, and the warnings and so on that we saw on Windy. So yes, we have lots of things, but for time being, there's no, how to say it, it's not yet defined a NAVTEX subset here. Okay, so it's feasible. We will not go through all these subject codes. We have lots of possibilities with Navdat, and it's certainly possible to transmit just text messages also with Navdat. Okay, which brings me to the next slide. So this is a little bit, yeah. Well, so if you look at it, you know, it's not exactly like this, because for time being, it's the NAVTEX subset is not really defined yet in Navdat, but NAVTEX would be the subset of Navdat. Okay, and this is true for the data. Okay, for the data services, but it will also be true a little bit for if you look at it from a transmitter side. Okay, so a transmitter, a Navdat transmitter, could transmit a NAVTEX message, NAVTEX standard message, but a NAVTEX one is way more difficult, what we discussed before, to transmit a Navdat message. Okay, so if we sum it up on this one, will it replace NAVTEX? In the future, maybe. Okay, but, and this is an important message, NAVTEX continues to provide critical service. Okay, so we have lots of NAVTEX services around. You know, you saw the example from Jos Hardling. The ships have the receivers. Okay, so it can be received everywhere. So it will be around for at least for the next 10 to 15 years, because we have the infrastructure is existing, the receivers are existing. So it will not replace one, but it will be there will be a transition phase. Okay, for sure. And it also means for a Coast Guard that has, for example, obsolete NAVTEX transmitters, you can still buy NAVTEX transmitters. It's not, don't worry, it's not, you will have enough time to use it before NAVTEX will be phased out. Okay.
Great, thanks, Hermann. And so I think this is the last of our consideration. This one says Navdat is a mature standard. Let's see if one of you can speak to this then, please.
Well, sure. Maybe I'll take this one on. You know, first of all, you know, what do you mean with a mature standard? You know, there's different takes on that, but let's maybe just look back and where it came from, some of the evolution of the standard. And initially, it was inspired by the Digital Radio Mondiale standard, which is optimized for medium wave AM broadcasts. And it is intended for audio broadcasts for, you know, your AM radio. And it is very widely deployed in India. Nautel has supplied many medium wave transmitters into India, the biggest installation of digital radio all across the AM medium wave band. You know, and but over the years, you know, Navdat is no longer DRM. It shares some of the physical parameters with DRM, but it has evolved. It has been, you know, adapted for maritime communications. So the 1 kHz and 3 kHz bandwidths, for example, are not present in the DRM modes. Those are only present in Navdat. So that would not be compatible. The data encapsulation, you know, the messages we're sending are very much tailored to maritime communications, and it wouldn't really have much application in a typical, you know, commercial radio broadcast. And new modes and guard intervals are adapted, and there's a new forward error correction, the low density parity code LDPC checks. That also help with some of the range. But on the left here, I just want to show one of our NX transmitters. Those are our AM transmitter flagships. And you know, you can see there's a DRM spectrum. It looks very similar to the Navdat spectrum, but not quite. You know, in this case, typically we deal with 18 kHz bandwidths, 9 kHz bandwidths, but there's also 10 kHz modes as well. So perhaps the DRM could serve as an initial proof of concept if you needed to see where coverage goes, but in the end, the two standards are diverging, and that becomes, of course, more important as we deal with the application. So maybe next slide. So, you know, in terms of mature standard, I think we need to take a step back and look at the overall technology rollout. Standardization is only one part. It's the head end of a longer roadmap. You know, so at this point, you know, standardization is moving along. I believe next year we could see a first official version of it that might go further. However, as this process is going on, I would not be surprised if there would be enhancements and improvements and maybe slight modifications going forward. That's what's typical with other digital radio introductions. Today, the physical communication layer is quite well defined. And that means, you know, we can start to look at high power NAVTEX transmitters. We have an idea as to what the signal looks like for transmitters. We can design for it. You know, the physical communication layer allows for sea trials. Typically we call them field trials, but I figured for NAVTEX it's more appropriate to call them sea trials. With, you know, China and France already having conducted some initial tests. But really, I think we need more field trials to better characterize coverage across many different modes. That will then, you know, help with the coverage planning. So I see initially select high power transmitter test installations for that. And with that, we also need initial experimental receivers so we can really get a good understanding of what coverage we can expect. The sort of thing that we need to look at next, you know, as we're starting to think about deploying NAVTEX, is really think about your stakeholder needs. You know, look at the promise of NAVTEX and what does it matter to your country, to your jurisdiction. You know, does your country care about ICE reports? Maybe not. Maybe piracy is a bigger concern for you. Maybe other messages are more important, and have a look and see what sort of messages you might need to convey and what data rates you might need on or impose on the system. You know, maybe there's other applications that haven't been covered by the standard. There is a number of reserved message types that could be used for specific applications that are still available for extension. And another thing is, you know, the standard does allow for Mayday relays, for example. If that is something important to you, then perhaps you need to think about 24-hour coverage rather than time slots. And perhaps in a follow-on session webinar, we might talk about how single frequency networks, having all your transmitter broadcasting the same frequency at the same time, could potentially accomplish that. So that's another thing to think about. Then knowing what data rates and coverage you need, that's when you can start the coverage planning. And you need to take your geography and your data requirements into account. After that, you know, as we're starting to look into more serious deployments, you will likely see professional monitoring receivers hit the market. You know, the more expensive non-consumer grades, but needed for your shore stations to monitor the transmissions. You know, those will probably be next. And, you know, only once those pieces are in place can I see countrywide transmission installations where we overhaul a whole network potentially. And you need to think about, do we need new sites, new towers, new transmitters, new ATUs? And really, I think the technology really only becomes mature when we get commercial receivers into mass production. And we can look at other digital radio standards, and particularly thinking of, you know, DAB in Europe, digital audio broadcasting. And it has really taken advantage of the mandate of every car sold in Europe having a DAB receiver built into it. Do we need to have similar rules like that once we have achieved significant momentum in the standard? You know, those are things to think about. So I still consider us to be in more or less the developing part of the standard, but looking towards deployment. But you know, I think it will take a few years before we really get into a mature system that will benefit everyone. So next.
Great. Thanks, Philip. Lots to digest and think about there. That closes out, I guess, the most of the content that we wanted to cover. Just in summary, you know, we feel that NAVTEX needs a system approach. Think of your transmitter, but also think of your ATU and your site and your antenna. Think about bandwidth. There is this tight relationship between power and coverage and bandwidth and the data rate. Those all need to be considered. I think it's obvious that NAVTEX will continue for many years to come. And some of the thoughts that Philip just talked about in your thinking of deployment strategies. Do you need separate NAVTEX and Navdat infrastructures? Think about the goals that you want to achieve for your Navdat. How can you learn more? We will hope to continue this series of webinars with maybe looking at a deeper dive into the signal at some point in the new year, maybe looking at coverage. You're certainly welcome to reach out to Nautel and Kenta if you'd like to discuss any deployments or assessments that you're thinking of doing. I'm also going to switch it over to questions. We have a few that have come in, but just a reminder, if you click on the orange bar, it exposes the control bar and you can enter a question and we'll see if we can respond to those. Several have asked, will the slides be available? We will make this whole recorded archive version of the webinar available on our website. Typically, we may get it up within 24 hours, but certainly before the end of the week. I also have a question here and see if I can relay it clearly. It sounds like it's a question about the type of modulation for Navdat, if it's FSK or PSK. I'm not sure if Philip or Hermann, if that.
Go ahead, Phil.
Technically, and perhaps we should have mentioned that Summers in retrospect, but the modulation scheme is called orthogonal frequency division multiplexing. And what that is it will align multiple carriers, 229 in our presentation, side by side. And this particular modulation scheme, and that is used in DRM, as we mentioned from the background, HD radio, DAB, DVB, all the modern communication standards use OFDM. Now, OFDM only tells you that the carriers are side by side. Then the actual modulation on it is, as in Hermann's section he was talking about, we will modulate both the amplitude as well as the phase. So it's no longer frequency shift keying, but we modulate the amplitude and the phase of each fixed carrier. So you can think of it as phase modulation, if you like, and amplitude modulation.
Thanks, Philip. And we have a couple of comments here of people appreciating the content of the webinar, and well, we thank you for joining us today. And there will be just a brief questionnaire at the end of the webinar. As you close out, we ask you to share your feedback. That's the only way we can make sure that we're putting the right content together for you and making sure that it's useful of your time. So with that, I think that's going to be the rest of the questions today. I'm just going to say thank you very much to our audience from across the globe that have joined us today. And we look forward to speaking to you again soon. So thanks from the Nautel and Kenta team. You have a great day.